Okay, now let's look at another factor of finding conditions that are optimal for enzyme activity, and that has to do with pH. So very often one of the things that's commonly reported for a purified enzyme is its pH profile. And the pH profile of the enzyme shows you some good information, right? It shows you stability of the enzyme, right? So this shows you basically the ranges at which you maintain activity. So we could do activity assays at different pH level, and we can also do like a pure stability assay where we look at folding, maintaining folding of the enzyme at different pHs. And one of the techniques that can be used is circular dichroism spectroscopy, or CD spectroscopy at different pHs, and that gives you an idea of the folded state of that protein. You can also look at changes in fluorescence, right, as that protein is going to denature. So anyway, there's two lines on this graph, and I just wanted to point out this idea of stability of the enzyme at different pHs. So you could look at the functional stability, you could look at the structural stability, and that's why you've got two lines here. So, so if we look at the activity, is shown by the black line. And if we look at the structural, right, the broader pH stability, they're talking about the structural stability. Now, if you look at inflection points, and so if we're just looking at enzyme activity, and if you look at inflection points represent pKa's of catalytically important groups. So this is another very important piece of information you get from performing a pH profile for enzyme activity, because you can determine what are possibly your important catalytic groups. And so we're looking at, again, our musical amino acids, DDD, la la la, aspartate, glutamate, arginine, lysine, histidine. These are common amino acids that need to be either protonated or deprotonated in order to aid in substrate binding or in catalysis. And we could also look at the pKa of different cofactors. Like if we have a flavin cofactor, we could look at pKa for an ionizable nitrogen on that flavin ring. So at any rate, we get some information about what might be a catalytically important group on that enzyme. Of course, if we go too far in either direction, we're changing the hydrogen ion concentration of the system. And so when we change pH, we change ionization state of different catalytically important groups and also structurally important groups. And we can change, right, ionic interactions that are important structurally. So salt bridge interactions that are important for holding together, the tertiary or quaternary structure of a protein. And we can also change ability to hydrogen bond, right? So anyway, this is the general idea for how change in pH can destroy protein structure, because we're changing ionization states and we're changing abilities to form weak non-covalent interactions. And then there's other factors of an enzyme assay, which we're not going to focus on so much, that are important when we consider maintaining good, weak non-covalent interactions and hydrophobic effects. To keep that protein folded properly, we have to consider also ionic strength of the assay. So basically the saltiness of the assay. And this again can mess up our ionic interactions on the protein, because we can have ions that shield different positive and negative charges on the protein and cause this structure to unravel. And we have to also consider the let's say that the hydrophobicity of the solution. So we need to maintain, right, the proper aqueous environment for our proteins. You know, most proteins are going to be soluble in the cytoplasm, and they're going to like an aqueous environment. You know, proteins don't exist on their own. They're very social. They like to be in this crowded little compartment of the cell where there's lots of proteins. So sometimes we might have to add excess, you know, binding proteins to our system, things like serum albumin, just to keep the enzymes happy. But for the most part, enzymes like to have an aqueous environment, unless we're looking at enzymes that are associated with cell membranes, right, or organelle membranes. And then we're going to have to provide some more hydrophobic nature to the enzyme assay buffer in order to keep those particular proteins happy. And again, because if you add you know, a hydrophobic solution to your assay, so if we add in a lot of, let's say, you know, a longer chain alcohol like propanol, right? If we're adding propanol into our system, we can cause a greater hydrophobic nature to our solution, and we can start to have that protein unravel because we're giving it a way to replace hydrophobic interactions within the protein with hydrophobic interactions with the solvent. So let's go on. Once you've found the optimal conditions for your enzyme assay, you need to make sure that you're using that assay within the linear range. And we always want to assess enzyme activity within the steady state. And so in the steady state of a reaction, we have still unlimited substrate, and the change in concentration of our enzyme substrate complex is going to be pretty much constant with time, right? So there's not going to be any change. Okay, so let's look at our graph. So our x-axis is always going to be time, right? So these are kinetic assays. So we're always looking at something with respect to time. And that could be seconds, it could be minutes. It depends on what enzyme that you're looking at. And we're looking at product formed here. And they're not telling you, but usually we're looking at this in terms of concentration. And at this point in the assay here, where it's the yellow triangle, this is a sweet spot. This is where you want to be working. This is the steady state. And how do we know that it's the steady state? Because the rate of change of product, right, the rate of accumulation of product is, you know, with respect to time, is going to be your velocity. And this is, right, V naught. So I'll write it larger so you can see it. That's V naught. Okay. And at this point, we have constant velocity. V naught, initial velocity, is constant over a particular amount of time, but the yellow triangle shows you what is your steady state. And you always want to make sure that you're only taking your measurements of enzyme activity in the initial part of the curve, and it's got to be linear. If it's not linear and you're doing a continuous assay, you'll see it immediately because you're monitoring the formation of product in real time. But you need to also make sure that you're working in the steady state where you're doing a discontinuous assay too. So you only work in this area. Why? Well, think about it. If you're working in the red zone, right, the red line up here, you don't want to work up here because you're going to get incorrect, non-valid measure of your enzyme activity. So if you take a measurement of enzyme activity here, you're getting a falsely low measure of enzyme activity because you're measuring this much product and you've already entered into the phase where you've departed from the steady state, right? This is where you depart from steady state. And what's happening when you depart from the steady state? A couple things are happening. You're depleting substrate. You have too much product, and maybe your enzyme is subject to product inhibition, possibly. Maybe the product of that enzyme is not necessarily competitively inhibiting the enzyme, but maybe it's an acidic product and it's changing the pH of the solution, and your enzyme's just falling apart. You're destroying the structure of that enzyme. So it could be product inhibition at the active site, it could be acidic or basic, and it's just mechanically screwing up your enzyme because it's causing your enzyme to unravel. And the other thing that happens too is, some enzymes are pretty fragile, and we know with the induced fit model, and that enzyme is going to be flexing, maybe the enzyme is just mechanically wearing out. And so you're just losing enzyme activity. So these are a couple reasons why, an enzymatic reaction in the laboratory can't go on, forever and ever, although we can use some enzymes to make particular products for us if we keep those enzymes in a protected space, and we're constantly feeding fresh substrate and drawing off formed product. And we could do that with a special type of flow dialysis. At any rate, there's one thing I want to mention to you that I forgot to tell you about, and it has to do with this concept of the pH optimum of an enzyme. So one of the things that I didn't mention to you before, and thinking about the green ink made me remember, this is the band of physiological pH. And so we have different physiological pHs within our bodies, right? If you think about different organs, right, maintain different pH environments within the lumen of those organs. So just think about your digestive tract, right? Stomach, highly acidic, duodenum, pretty basic. So, and then we have the blood, right, which is pH 7.4. But even within a cell, we have different pH profiles for enzymes that are found in different cellular compartments. And if I can find it, I'll pull up the picture for you. But at any rate, we find that enzymes, even though they might be working in an area within the cell that is pH 7, they're actually going to have a broader allowable or tolerable pH range for activity than simply the pH of the compartment at which they're active physiologically. So just keep that in mind.